Welcome to Neurosalience, the OHBM podcast. Today my guest is Dr. Audrey Fan, assistant professor in the departments of Neurology and Biomedical Engineering at the University of California, Davis. She also serves as co-director of the Imaging Core for UC Davis's Health's Alzheimer's Disease Center, which is an NIH-funded Alzheimer's Research Center. Dr. Fan is an imaging physicist and translational scientist. She develops novel magnetic resonance imaging and positron emission tomography methods to study brain physiology in cerebrovascular disease and vascular dementia. She has translated new imaging technologies to patient studies in acute stroke, Moyamoya disease, and intracranial stenosis. She received her bachelor's from Stanford, then her Ph.D. from the Department of Electrical Engineering and Computer Science at MIT. She returned to Stanford for her post-doctoral training and recently moved to UC Davis to start up her own lab. Dr. Fan is one of only a handful of researchers who are wielding MRI to non-invasively extract with ever more effectiveness useful quantitative information about brain physiology that's also clinically relevant. This includes not only quantitative flow, volume, and oxygenation, but also cerebral metabolic rate and oxygen extraction fraction to help guide treatment and therapy for stroke, vascular dementia, and other neurovascular disorders. This, in my opinion, is such an important area to work in, as MRI is so sensitive to so many physiologic variables with such a broad parameter space to work in. Even at about 40 years old, MRI has untapped potential and clinical efficacy, which Audrey is working to utilize. Our conversation, I think, gives a good perspective of the unique challenges and opportunities of this exciting subfield of MRI. So I hope you enjoy it. Okay, welcome, Audrey Fan, to the OHBM Neurosalience podcast.
Delighted to be here.
Yeah, great. So you're an expert in. You have your degrees in engineering. You've worked in the technical side, and you've been working on something that has been close to my interests but you've taken it much further towards clinical applications. And that's sort of extracting more quantitative information from MRI and in the context of either fMRI or MRI itself, and more quantitative physiologic information that's relevant. I mean, so for us in the field of fMRI, we mostly work with bold contrast. And for a while we cared a lot about understanding bold just because we wanted to interpret what was going on neuronally. And, some people work with arterial spin labeling. Some people might use susceptibility maps like SWI to see where the veins are. So now we're going to talk about your work.
Thanks for that overview. And, as you pointed out, I think one of the problems that I have pursued throughout, my time working with MR and my research career is to try to extract quantitative information about brain oxygenation. So, that entails, trying to understand both from veins, but also now more on the tissue side, what is happening in terms of oxygen extraction, what is the oxygen metabolism, because our brain is so uniquely energy demanding, and there's no way to store this oxygen supply in the brain. There's no natural reserve. So I think it's a interesting physiological, and you can imagine we have no supply to reserve to speak of. And so with the clinical impact, anything that could potentially put this oxygen delivery or metabolism at risk, right, is going to be a really important clinical question as well. So I think this has always physiologically and clinically motivated me, but as you pointed out, I'm an engineer. So I think actually beyond that, what has interested me the most is just how hard it is. And I think there's there's a reason for that. I mean, for instance, a lot of the source of contrast, which is very familiar to the podcast listeners, deoxyhemoglobin, right? That is still essential in terms of many types of contrast mechanisms that will eventually allow us to quantify oxygen metabolism. But if you think about the component in each tissue voxel, for instance, of the brain, that is actually blood, that actually would have deoxyhemoglobin, it's very small. So we
Yeah.
have signal to noise issues. And because the type of sensitive contrast that we get with MR often reflects so many different processes, right? The modeling gets really complex too, right? So dealing with those two technical problems right off the bat, right? It's daunting, but as an engineer, or maybe naively as a PhD student, I thought this is a perfect problem to tackle, and it could make a real big impact.
Yeah. Yeah, and I like the way you set it up because it's like it really is a hard problem, but there's just enough measures that you can actually get at an answer. I mean, it seems like you can, for instance, with bold. I mean, of course, people worry about the hematocrit, and they worry about the blood volume distribution in each voxel, and that affects the bold signal, and perfusion, of course, and then so you if you get all that information, then you can infer how much oxygen is extracted. I guess that's the sort of at least to me, the basic concept. It's hard. It's really hard, but to extract that information though is really clinically useful. And so I just like to start a little bit with, and it's interesting. I forgot to mention one other person's like going even prehistory of all this stuff. I think one of the first people who really cared about, well, aside from Ogawa, of course, but Keith Thulborn, he was the first person to say, hey, there's hemorrhaging there. There's blood. This is potentially useful to use this more. So, but it's come a long way since then. And I first wanted just to point out, we won't go into any detail, but a really, really nice, when I was preparing for this podcast, this is one thing great about, for me at least, when I prepare for these podcasts, is that I'm forced to look at the literature in a way that I wouldn't otherwise. And I discovered this paper, which was just wonderful, that you co-wrote with Claudine Gauthier in Neuroimage in 2019, titled "Bold Signal Physiology: Models and Applications." And just going through it, it's pretty comprehensive. I mean, you show dynamic models with Rick Buxton, you talk about bold signal models, and then you really kind of set up really nicely the calibrated fMRI models, the assumptions, the hypercapnia models, and going from there, you talk about how there's even progress in looking at baseline oxygenation or baseline CMO2. And then you talk about your vascular fingerprinting, which we'll talk about at the end, which is also really exciting. So I just wanted to point this out, that it's and also you talk about potential clinical applications of all this. So maybe before we get into your papers, just off the top of your head, so what are the pieces of information that you're trying to extract or that you have been able to extract, and how is that potentially useful in different clinical settings, like with maybe stroke or whatever?
Yeah, I'll jump back to the brain oxygenation example, just because it is an anchor that's, I think, really relevant in a whole range of cerebrovascular disease. But I think in the acute stroke setting, or in severe, for instance, cerebrovascular occlusion, you would expect a change in oxygenation, but that's actually hard to predict, right? So in terms of the measures that we're able to acquire, you had mentioned MR has the potential to be sensitive to all these different physiological processes. Perfusion is, for instance, with arteriospin labeling or dynamic susceptibility contrast. I mean, that's one side of the coin, the delivery of blood flow to the brain. But why am I working on other measures and other physiological metrics? I think that's not the whole story, because you could have low blood flow, but you could have really great collateral patterns if you have a chronic occlusion. So if one major stem of your artery has a slight occlusion. You might suffer reduced blood flow, but you might also have these tiny, twisty collateral vessels that still deliver oxygen, right? And so if you don't have, for instance, both sides of the coin, the delivery and the extraction of oxygen, you don't see the complete picture. And classically, and this is going back to older PET imaging, a high oxygen extraction fraction is kind of a hallmark of risk. So if a tissue is at risk of low perfusion and it's trying to compensate, so, OEF classically from oxygen 15 PET experiments has been a hallmark of risk and tissue that is potentially destined to die, right? And so, if you can look at these measures in tandem, you can build, for instance, physiological models of a cascade of what's happening during chronic occlusion or even evolution of acute stroke over the course of, say, 24 hours. And I think that also has clinical impact because now more and more imaging can act as a way to stratify patients for treatments. So a lot of times, treatments such as clot buster drugs for acute stroke, they come with potential risks as well. So for instance, potential risks of hemorrhage, and so there's these established, maybe hard to shift clinical paradigms of time to treat, for instance, for acute stroke. But if we have imaging information, and in particular, if we have specific physiological information that is directly applicable about the state of the tissue, the physiological state,
Yeah.
is it at risk? Then you have a much better idea of whether the patient's a good candidate for treatment.
Yeah. So along those lines, really, I just have a quick interjection about that. So this is someone has a stroke, and the oxygen extraction is like if the tissue is viable, if you have low flow, it might be a high oxygen extraction
Yeah.
fraction. And if the tissue is dead, then there wouldn't be much oxygen extraction. It would be lower. And so you can get that information and make a decision. Well, is it worth, yeah, I guess doing that, I guess. Is that, yeah.
Yeah, certainly, and that's another reason why you need these multiple measures because oxygen metabolism is dependent on the product of both your delivery and your extraction, and there's a severe disease threshold where your overall oxygen metabolism starts to go down, exactly like you said, because neuronal death is happening. You're not getting the blood flow, and you're not extracting it because your neurons are dying. And
Yeah.
so I think that's exactly the type of chronic or progressive cascade that we can build once we have this sort of quantitative information. And just speaking a little bit more about quantification, right? I think the other thing that tackling this hard problem of putting some numbers down, quantifying, getting more specific measures, it also allows us to look at more subtle processes that happen with time, like during aging processes, with dementia, where you don't necessarily have acute or severe occlusion in a particular vessel, for instance, but you might have systemic peripheral vascular disease or systemic atherosclerosis that overall, over time, will eventually contribute to cognitive aging.
Yeah.
And I think characterizing the physiological impact of that is in a different realm because you're not going to see these huge or focal OEF oxygen extraction changes. But if you can quantify with some degree of certainty how it changes over time, then you can use that information to design, for instance, lifestyle interventions for diseases that traditionally haven't been thought of as vascular, but
Yeah.
we're learning that actually there's a huge vascular contribution to dementias and cognitive aging. And so I
Yes.
think both acute settings and more subtle long-term impacts of cerebrovascular changes are important and could benefit from these sort of methods.
Yeah. So, so initially people might think, okay, why not just do, I mean, certainly there's invasive measures like gadolinium, or just do arterial spin labeling, and then you can just look at perfusion. And so you could, but so why would you need, and of course you need quantitative perfusion because, and it's important to sort of emphasize that because, each time you do a scan, the calibration for the the gain and everything like that is different, and things can be different, and you can't really, if you unless you're quantifying, you can't really compare as well, just because of the nature of MRI. So what do you need more than just perfusion to get at, like, for instance, vascular dementia? Um,
Yeah, I mean, I'm biased, but I do think the oxygenation and perfusion coupled together give us a more complete picture of oxygen metabolism and what's going on. And in
yeah,
particular, if it's hard to directly visualize an image, for instance, collaterals or other compensatory mechanisms, this is a way that we can look at both sides of the coins, at least on the oxygen delivery side, right? And I think others might have ideas about cerebrovascular reactivity in combination with blood volume as alternative measures. But I think from the perspective of risk, at least developing that from the acute stroke paradigm and perhaps parlaying that into more subtle vascular dementias. I still think looking at both oxygen extraction and the perfusion together, I think that in and of itself is a more complete picture, which not many sites are collecting and not many clinical hospitals can have access to at the moment.
yeah, yeah, and that's actually right. I mean, typically you need PET scanning for this sort of thing, which is extremely expensive, requires a cyclotron and all kinds of things, and it's not something that will be clinically, common. Whereas this, it's non-invasive. Uh, uh, well, I mean, so what do you just generally, for instance, to extract baseline oxygenation, what do you need to do? I mean, there might be some stresses like breath holding or things like that, and so maybe you might want to just mention kind of what it takes a little bit.
Yeah. And I think what it takes depends on the method, the contrast that you're pursuing, because as this field has evolved, there's actually multiple options on the table. And I think that's really exciting. And part of my work has been trying to compare these different methods to understand the relative pros and cons. But every approach has its own model assumptions. I would say every approach has advanced modeling, and so it's really important to just keep in mind what are the considerations and what are you trying to get at. Are you trying to get at local information? Are you trying to get at a global oxygen signal that's reflecting the whole brain's output, basically the venous output? So one example of a way that I've approached oxygenation imaging, and this is the crux of my PhD work, is looking at phase signal in MR. And I think that's been undervalued. Most of the time, we're looking at these beautiful contrasts based on magnitude images. But the MR signal is not just a scalar. You can think of it as like a vector that not only has an amplitude, but it has a direction. And it works out that this direction, this phase angle of the vector, gives us really valuable information about underlying tissue properties. And in
Yes.
particular, susceptibility, magnetic susceptibility, that is directly related to the oxygenation state of your venous blood. And so, what I've done in my early work is take a look at phase images and see if I can use phase differences inside the vessel, where I know if it's a big vein that there are deoxyhemoglobin inclusions and concentrations compared to the tissue around it, or compared to something that doesn't have deoxyhemoglobin like cerebrospinal fluid. And that modeling is challenging
Yep.
because it depends a lot on the size and orientation of the vessels.
Yep.
So part of the struggle I faced, and I think we've done a lot of investigation, is how can we make this more complete and not model vessels as dinky little straight cylinders, because we know they are not straight cylinders. How can we extend beyond that to something that's more realistic in the brain of the vasculature? And also, how can we deal with partial volume effects in a way that is still going to be highly accurate to what's happening in the brain? So
Yeah.
that's one example of a contrast mechanism where It's not directly related to bold, but I can use the phase signal and model the vessels in a advanced way so that I tie the phase signal to the deoxyhemoglobin and therefore oxygen extraction in the veins.
And so let me just quickly, and obviously I'll catch myself in trying to get too in the weeds, but yeah, trying to model this, right? I mean, you have, the orientation affects the phase intravascularly as well as extravascularly, but then I also worry about a little bit, just the basic blood flow velocity that might cause a phase shift or something, just for different reasons, velocity reasons. But it seems that right, and I like the idea then of trying to step back and this is sort of like along the lines of your vascular fingerprinting. I'm thinking maybe similar that where you just assume like a random distribution and then the decay has very different signatures depending on, and we'll talk about this a little bit later, of it's fundamentally in the phase, but then it's phase dispersion, then it's back to the magnitude if it's small enough. But anyway, yeah.
Yeah, no, I mean, I think you're exactly right. The velocity definitely matters in the blood. We try to use flow compensation, but man, our big arteries, like I've seen these beautiful pictures of the sagittal sinus, for instance. This is really large draining vessel that's the output of a lot of those surface cortical tissues or peel vessels that drain into this big trunk of a vein that exits out the back of your head. And that's a perfect spot that many uh, both phase-based and T2-based measurements of oxygenation, if you wanted to just target one global signal representing the whole brain's oxygen extraction output, that would be a great target.
Yeah,
But especially for the phase measurement, I mean, not only is there faster velocity in the big vessels, even pulsatility. I've seen these beautiful pictures of the sagittal sinus actually pulsing. So there's a lot of artifacts and a lot of assumptions that are always going to be there. But I think in the long run, we're always trying to make progress, and the question is, can you just advance it in a way that it's also clinically meaningful, right? So it doesn't make clinical impact to address every single artifact, potentially not, right? Is it more important to be able to be sensitive to a difference in a patient population rather to get the perfect, exact, accurate number, right? So there's always a trade off, especially with model complexity. But I definitely appreciate your point that, hey, there's blood flow happening, there's probably pulsatility, and that's the beauty of the system.
yeah, yeah, exactly. And yeah, no, and I think that with all the work you've done and others, I mean, it's people are becoming much more confident in these types of measures and the ability to, yeah, it actually does work. I mean, the MR phase is sensitive to oxygenation, and
Maybe I'll just jump in too. And that method, from the way that I've described it, maybe I didn't emphasize this, but it's actually comes for free in some sense. So if you're acquiring a susceptibility weighted or a gradient echo image, I mean, you're already collecting the magnitude component. That signal vector that I was talking about, that phase is part of it, and we're intrinsically collecting it. Let's not throw it away, right? So part of what I loved about that aspect of my PhD is just almost like another person's trash is, my treasure that I can transform into something meaningful, and that was really rewarding for me. And in that sense, with the phase-based oxygen metabolism measures, there are a lot of assumptions about vessel orientation and geometry, but it doesn't require additional scans. So you can get a baseline oxygen measurement in a vein that you can resolve. You could run the scan again in a different condition or on a different day, and that would reflect a different state. So,
yeah,
kind of like arterial spin labeling, I can envision this as a scan where you get one snapshot for one physiological state. You don't have to combine multiple ones to eventually get an oxygen metabolism, if that
yes,
makes sense. Yeah.
yeah, 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 exactly. Which is nice in that regard, where you can actually do this snapshot and do this multiple. So just a quick, so looking at even, so you got the MR phase and you have perfusion. Uh, so, it's funny. I even, when I talk to my colleagues here who do gadolinium studies and look at perfusion, they always like to say, oh, ASL isn't sensitive enough. We can't, doesn't make sense to do that. We can just do gadolinium and it works. Well, of course, gadolinium is invasive. And I do think that ASL, especially, and also they worry about not only the sensitivity, but, and this is something you addressed very well in your papers, the different transit times
Mhm.
sort of affecting interpretation. And you can adjust you can do multi-delay ASL, and that's pretty much. And also, there's different types of velocity selections and things like that. And so that's actually works really nicely. And so, do you think that? I mean, so you're scanning at 3 Tesla, and with the multi-channel acquisition, I mean, and the images that I've seen in your papers look great. And so, it seems like it's good enough for clinical use. Uh,
I think
uh,
it depends on, if you're talking about the oxygen mapping onto veins that I've
yeah.
worked a lot with. I think it depends on a priori understanding of which veins are pulling blood, venous output from which parts of the brain, which I think is still not well understood. And part of that is because actually I believe there's a lot more individual to individual variability in the venous system. And also, when people have learned a lot about either brain functions or what happens in disease, often something bad or pathological has happened. On the stroke side, a lot of times the stroke happens in arteries, right? There are, venous thromboses, but for the most part, we think a lot about strokes in the arterial side. And so I just think the venous system, not only is it more variable and inherently biologically, but we just don't have clinically also as much of an understanding of how it drains different part of the brain tissue.
Well,
So
that's
the
interesting.
question, yeah, the question of, is it good enough for clinical use? I think it depends on the region of the brain that you're interested in, how big or small it is, and therefore, do you have the time for scanning to achieve a particular resolution of vein? Um,
Yeah. Yeah. Okay. Okay. That's interesting. I mean, yeah, I would love to do like ultra high resolution. It's uh, doing a quantitative oxidation map to see how actually the numbers change as you go to like 0.5 millimeter resolution or
yeah.
it's, where you can actually potentially look at further down the vascular tree to see or it's further up it, I guess, towards the arterial or into the capillaries. But yeah. So okay, so all right. So so that's pretty much the there's other strategies, and I won't even talk about them. There's Hanzeng Liu has a method where he does arterial spin labeling, but then he measures the oxygenation in only the perfusing blood. It seems to work, but this works just fine too. And yeah, so how do you get around? So as far as solving the problem of, so you said that at least keeping on looking at the phase, can you get a better estimate of like the geometry then, as far as trying to predict the oxygenation from the phase? Is there ways of is do you increase your certainty in terms of the geometry, or do you just try to generalize across geometric configurations? Um,
That's a wonderful question, and it was the crux of the reconstruction problem that I had the great fortune of working with my lab mate Barkin Bilhik when I was a PhD student, and he's now an assistant professor at Mass General Hospital. But we really kind of grew up, and we're doing our PhD work during a time where quantitative susceptibility mapping in MR was just ramping up. And what this subfield of MR, this technique attempts to do is give you a map based on phase inputs. So if I give you a 3D image of this phase angle from the
huh.
MR experiment, can you give me a map of magnetic susceptibility? And this, you can imagine the forward transformation is really easy. So if I tell you what the susceptibility of each tissue is at any given location in the brain, including the vessels that I'm most interested in, then I could do a dipole kind of convolution and do a forward simulation. Hey, here's the field map, here's the phase that I would expect. But the inverse problem, no matter what sequence you're using, is actually ill-posed, meaning we're missing data. And so a lot of the problem we were trying to tackle is, okay, can we get a 3D susceptibility map which would remove some of these dipole or blurring issues and
Yeah.
therefore give you better visualization of the veins?
Hmm.
That required some fancy prior information and specialized inversion algorithms that I had the great fortune of working with Dr. Bilhig to build and optimize, in particular for veins. And there's some clever tricks you can do. So, for instance, in terms of prior information, you can say, well, the veins, I mean, we're trying to reconstruct something that's more accurate and faithful to where the veins are based on susceptibility, but on a gross level, it should also kind of look like the magnitude image. So if you take the first spatial derivative, you kind of look at the edges of the magnitude image to see where the veins are. You can kind of use that as prior information to help with this mathematical problem. I'm
Okay.
talking a lot of jargon here, but in the end, what you get out of it is a 3D map, and that 3D map of susceptibility, um, that field itself has evolved quite a bit as a method. And I think one of its great potential is in visualizing veins, especially at high resolution, um, and beyond visualization, telling you what the magnetic susceptibility due to deoxyhemoglobin is, regardless of what the vein's orientation is. Um,
Okay.
it's not perfect. There's
Yeah.
still biases with orientation, but I think that was a serendipitous but really parallel development of physiology imaging and susceptibility mapping as a technique.
Oh, that's very cool. That's very cool. What about there's other sources of susceptibility. How do you look around those? Like, for instance, iron deposits, or there's neuromelanin, there's iron, there's all kinds of things. How do you? I guess you know where to look. They go to certain spots, but there could be some in gray matter. And is that a problem if you're trying to get baseline oxidation and then you see, and even at the edges of the gyri, sometimes there's susceptibility variations. Is that a challenge to work around that? Yeah.
Totally. And in particular, I've talked a lot about veins, but there are groups and extensions of this work where the susceptibility map has been used actually in tissue. And there you have to make assumptions about blood volume, which we talked about earlier in the podcast, how much of tissue voxel is actually coming from deoxyhemoglobin versus all these other things that you're mentioning, iron, myelin, etc. And it varies with gray versus white matter, etc. So I think
Yeah.
it's more of a problem when you're trying to look at the tissue and voxel to voxel level. But there are more and more clever ways also that people can use to address this. So there are QSM algorithm developments that separate diamagnetic versus paramagnetic contributions.
Yeah.
And myelin contributions often are diamagnetic. So, perhaps these sort of multi-channel mapping approaches, which, are a refinement to these algorithms, can help us in very challenging areas like tissue voxels.
Yeah.
Um,
Yeah.
mhm.
Oh, that's cool. That's actually okay. All right. That's actually, and so maybe I'll mention at this stage though. So you have, I mean, and this is one of the things that's also frustrating to me. So, and we'll get into some of the other methods too. But you have these amazing techniques, and it's obvious that they're sensitive to parameters that are very relevant to clinical applications almost immediately. And but now the question is, how does, and this is even a problem with a lot of things that are being developed on scanners, is how do you go from this sort of combination of pulse sequences and processing methods to clinical dissemination? How do
Yeah.
you, of course you have to have FDA approval and everything, but even still, I mean, uh, it involves, I mean, I guess the pulse sequence side could be okay, but there's certain manipulations, and then there's processing, and then there's a certain amount of care that a person has to put into it. Is that possible? And if so,
Yeah. No, I think this is a problem that many, many MR researchers face because whether you're more on the technical side versus, quote unquote, clinical side, we all, want in the long run for our sequences, our images to make a difference, whether for neuroscience or for patient care. And I've had the great fortune during my postdoc to work with, as you mentioned, Dr. Greg Zaharchuk at Stanford. And that was eye opening to me because Greg is a neuroradiologist, and I was part of a clinical department. And I think being in that environment really shifted my perspective, being trained as an engineer, right, to being part of a clinical department where I see grand rounds, where some of my colleagues sitting next to me at seminars are MDs. And for me, I think it really took throughout the course of my career a few brave and dedicated clinicians who were not afraid of techniques, especially techniques that were not quite ready for prime time, like disseminating with, you know, a standard software package. Nowhere near that, right? But if you can have a few clinical partners and work out a way to communicate what you're trying to do and integrate that into what their clinical decision making or what their radiological process is already like, I think that can go a long way, even in a small set of patients. And so for me, it was really being in the right environment that I had the opportunity to test any of my innovations out on patients.
yeah,
But over time, I also learned that the onus is on me as an engineer, as the technical developer. Early on, I didn't have that training, that clinical speak, so to speak. Um, and so I have to say, I did a really bad job of communicating why they should care, what it would take on their end, and how it would help their patients. I mean, these are very simple questions, but I just jumped way into the weeds with
yeah,
the
yeah,
methods. I was excited about it, right? But what excites the clinicians is something slightly different, right? So I think first and foremost that interpersonal relationship, being in that right environment, I can't emphasize how much that has helped shape my ability to translate
yeah.
these methods. Um,
Yeah, and that's a skill that's so underappreciated, I think, by many of the technical people. I think that's being able to communicate and kind of resonate with clinicians and or even cognitive neuroscientists or whatever. I mean, to sort of be in their world, clinicians, right? I mean, they're very, I work with radiologists here at the NIH sometimes, and they're very bottom line. They're like, well, what good is this? Is this is it quick? Is it? Can I interpret it? And
yes, they
okay, well then
should
I'll.
be.
Yeah, and then right, if it's too involved or if it's too uncertain, then they get very nervous and they just dismiss it. They don't have time for this. And but yeah, no, it is a very bottom line sort of situation. And also it's interesting because they sometimes don't care about as much as like if you're doing pure research on brain physiology, they might care about is it something that indicates a disease or not. And
Exactly.
so it's another slightly different way of thinking. But yeah, no, actually, so basically, I was just thinking in terms of so you have these methods, and so you're okay. So you have oxygen extraction fraction, which is clear the advantage of stroke, and actually looking at vascular diseases. What is the usefulness then of looking at? I mean, there's a lot of work on, and even in the context of bold contrast of fMRI, of looking at cerebrovascular reactivity. And you had a nice paper in 2021 with Greg Jaharchuk where you're looking at comparing that using a simultaneous PET MR scanner and comparing with O15 water. So first of all, why is PET the gold standard for CVR, and what information are you trying to extract with CVR? Because just one caveat that I think about sometimes when I look at bold contrast and people do CVR, it's very much weighted if they try to make a map of this, it looks like a blood volume map. It's like, well, you have a
Mm.
blood volume map, and so it's sort of weighted by blood volume, but you really want to get that quantitation of the reactivity, not necessarily the mapping, and the mapping, yeah, but can be indicative of right perfusion deficits. But yeah, I'll let you talk. Yeah.
Mhm. No, I mean, I think, it's like when you go to a cardiologist and they have you run on a treadmill, right? So sometimes the deficits aren't apparent until you stress the system a little bit. And so there are many different ways. I think you had other podcast interviewees who went more into detail. There's gas breathing, there's drug-based approaches. There's many ways to locally vasodilate, but also globally to the whole brain. And, that's a brain stress test in my book. And what we've seen in patients with intracranial stenosis using PET-MR is that your baseline blood flow is not always predictive of what your reactivity is going to be. And again, that goes to the fact that some people potentially have collaterals and other compensatory mechanisms that really aren't engaged until you give them this brain stress test, right? So
Yeah.
I think even if on some cases and in some populations a cerebrovascular reactivity map may look like a blood volume map. I don't believe that to always be the case,
Okay.
especially in patient populations. And personally, I've had a hard time, looking at a baseline perfusion image in intracranial stenosis and knowing what the reactivity is. And to your question about oxygen PET, so I've thought about this a lot, and in some ways, it is an old standard, not necessarily a gold standard, because there's many, assumptions and models that go along with oxygen PET as well. So as we're developing these oxygen sensitive MR quantification methods, we're also able to challenge potentially some of the underlying assumptions. So for instance, O15 oxygen PET has always kind of canonically said gray and white matter have very similar oxygen extraction across the brain. It's quite uniform. But is that really the case? Did old school
Yeah.
PET studies have sufficient spatial resolution to really look at deep gray matter versus surface gray matter, for instance? I think some of these questions are unresolved, particularly for blood flow. I do think O15 water, PET, is a good reference because it doesn't have some of these transit artifacts that you're describing. So with arterial spin labeling MRI, your signal really can change a lot depending on how long you wait between labeling the incoming arterial blood at the neck level to when you actually capture the image in the brain. And that
Yes.
can be hard to figure out if the person has tortuous vessels and it could take longer, or during even the reactivity experiment where this speeds up.
Yeah.
So actually, with the cerebrovascular reactivity measurements, we saw that decreasing this transit time was also problematic
Yep.
in terms
Yep.
of quantification. So it's, whenever you do quantification, I feel like every step you can learn something new, and improve the model. But you always also have to keep in mind, like as you said, the clinical impact and the bottom line.
Yeah.
Um, for us, I think the beauty of using PET MRI is that it really was, in my mind, the most elegant way to do a comparison with PET, because when you're doing any sort of manipulation, like giving a drug, uh, giving a gas to increase the blood flow, this stress test could depend a lot on the conditions of the day. So, was this person tired? Did this person jog 5 miles to get to the scanner? Did they have caffeine? Right? So many confounders could show up. But with
Yes.
PET MRI, we're exactly looking at the same brain physiological states and the same change, vasodilation, that we've created with this stress test. And so, I mean, I just would have a really hard time imagining, I mean, both logistically, but also physiologically, reasoning to myself that if I, had a person come in and I did the MR experiment with vasodilation and then had them come in a week later and did the PET imaging with vasodilation, did I really create the same vasodilation on both
Yeah.
days? I could try my best, but PET MR really allows me to know that it is the same. And that's the beauty, I think, for neurological research of the scanner, the hybrid scanner.
Yeah, yeah, and there's a number of PET MR scanners around the country, and I know that GE has really sort of pushed it in this regard, and so yeah, so I think definitely any experiment suffers from any repeatability issues, either due to subject state or whatever, or even doing a CO2 stress. You never do it the same way twice, and
Exactly.
so as far as the PET MR applications, is it purely to help? I mean, it's obviously not purely to help calibrate and compare against MR measures, but it's maybe I guess the initial vision was to collect really good and detailed MRI contrast and then compare that to metabolism. And that's also being done pretty much, right? Uh,
Yeah, I mean, I think that, some of the initial thoughts on PETMR improving image co-registration or just simply scheduling, facilitating two scans at once. I mean, that makes sense, but as someone who loves neuroscience and thinks about these experiments, it's maybe not satisfying. I
yeah,
think more satisfying contributions in brain imaging for PETMR include, like you said, this sort of cross validation of really hard methods for physiological imaging in the brain, but
yeah,
also metabolic to functional or functional to functional imaging that you just can't do. So, for instance, looking at neurotransmitter binding
yep,
with PET agents that you cannot do with MR unless you have a very specialized contrast agent, but
right,
correlating that to the bold response, right? So, can you build a model of neurotransmitter binding to the subsequent bold response? How does that change with different brain regions and different systems? That's
yeah,
something that PETMR can do simultaneously. That is
yes.
really challenging to do otherwise.
Yeah, yeah.
As,
And
yeah,
you have to,
yeah.
yeah, especially if you have to like titrate the amount, and you can get all that simultaneous information. That's okay. Okay.
Yeah, and I would also add that instead of directly correlating to physiological measures, another way that PETMR is helpful from a clinical standpoint might be, let's say you actually want to quantify something like amyloid buildup in Alzheimer's disease, and you have this PET agent for amyloid buildup, but really for quantification, you have this target range of 110 minutes. And to have the participant in there for PET scanning dynamically for 110 minutes, especially if it's an elderly participant, is really hard.
Yeah.
Can you
Yeah.
make that scan time shorter? Focus on the, say, second half or last 20 minutes of the scan. But in tandem with that, using PET-MR on the MR side, collect something like arterial spin labeling, know something about the delivery of the tracer without having captured that early part of the PET scan where the tracer was being injected.
Yeah.
So perhaps that could shorten scan times and still give you the quantification by combining something like PET binding at late phases
Yeah.
of the experiment with MR measures of arterial spin labeling, blood flow perfusion. I think that's also an underappreciated quantitative way to take PETMR in the long run.
Yeah. Yeah. The more I think about this, right. I mean, I think you're absolutely right. I think, yeah, there's all kinds of things that you could do with, right. I mean, looking at, injecting something and then, you're right. I mean, you could, if you have questions, I mean, I always have questions about, exchange rates and even blood-brain barrier sort of things. Right. If you could actually see a tracer and then somehow with MRI and then see it deposited with PET and then as you were saying also looking at for instance like binding, it'd be great to look at simultaneous if you were injecting some sort of drug or something and looking at the dopamine response and then looking at the corresponding fMRI activation. You could easily, I mean, there's so many things. I mean, Yeah, it's excited. Maybe I that's, but of course you need a cyclotron, and it's sort of
Yeah.
well, you may not always need a cyclotron if you're close to one or something, um, uh, but it's really, yeah, no, it's not only clinically useful, it's for research. It's extremely interesting.
Yeah, my feeling is that PETMR really shines in neurological and neuroscience research, and I think it hasn't reached its full potential there. So I agree with you. It's super exciting domain.
Yeah, I agree. It's a lot harder to build MR sensitive tracers that that are bound to specific molecules. It seems like PET is way ahead as far as that's concerned. All you have to do is have a radioactive sort of compound that's easier. Not It doesn't, people like Alan Koretsky always try to do things that are like susceptibility labeled things, but it's still hard.
That's good.
um, yeah, let me just maybe finish up a little bit with your recent work. It's in abstract form, and there's several abstracts that have been published over the last 2 years at ISMRM, and I'm really intrigued by it. And like a lot of things, it seems like it has a hint of things that people were working on, but then a new flavor and a new way to do it that's much more powerful. And this is called vascular fingerprinting. Do you want to describe, what that is, and why would you want to do this, and how you would do it? Yeah.
Yeah, this work, the idea and collaborations that came that led to this work also initiated in my time at Stanford with my colleague Thomas Christen, and now we're developing it further at UC Davis. So vascular fingerprinting is a way that is analogous to MR fingerprinting. So let me take a step back. A standard MR scan often will only collect one contrast for each scan, and that contrast is typically relative. So there was a Nature paper, I think it must have been 2010 or
Yep.
somewhere along that line,
Yeah.
where it feels like yesterday, but it's
I
actually
know.
a
I
while
know.
ago
When you
now.
mentioned it's almost a decade, more of a decade ago, it's like I feel like yesterday when I saw that. But yeah.
But the idea of MR fingerprinting is that some of these basic physical properties, such as T1, T2, relaxation, quantitatively, I mean, we know how to predict the effect of these tissue parameters on the signal. So if we have a particular sequence, whether it's a random sequence or a less random sequence, right, we can make a whole library and predictions of how a given combination of tissue properties will manifest on the signal.
Yep.
And so extending that, once you collect an image with that sequence, you have a library that you can match to. And now that sounds a lot like when you are a policeman and you go to a database, right? And you do fingerprinting and you identify a potential match for a victim or for a suspect. And once you find a match to a certain set of characteristics, in our case, signal characteristics, but fingerprinting, like, characteristics of the curvature of the fingerprint, things like that.
Yeah.
Once you make a match, you actually know a lot about that person. In
Yeah.
our case, once we make a signal match, you know a lot about the underlying voxel
Yes.
based on how
Yes.
you simulated it. And so we've taken this fingerprinting idea and put it in the framework of a microvascular voxel. So our simulations are not for T1, T2 per se, but taking a set of cylinders representing microvessels. It's similar in the way that we can assign parameters like the oxygenation in these microvessels,
Yeah.
the size of the radius of these vessels. And once we generate a whole dictionary, our matching to this signal library will now tell us vascular parameters. And so I'm really excited about this because for me, gives me a new approach to tackle tissue level oxygenation measurements on the microvasculature. Whereas before, like I mentioned, I was focusing a lot on big veins.
Yeah.
We still don't know exactly what part of the brain each vein is draining. I think those are still robust measurements that we can use to calibrate. But the vascular fingerprinting that we're developing now, I think, is a really cool model. It's a different model, and it could help us understand the tissue level oxygenation.
Interesting. Yeah. No, I like it. Looking at your paper, you have these wonderful, this very dense plot of all the potential, and so the sequence you use, it looks like an asymmetric spin echo and also a gradient echo. It looks like gradient echo, asymmetric spin echo, and on both sides of the echo. So you're looking at the echo train as it's falling, and then as it's rising and falling again, I guess.
Yeah,
And
exactly.
yeah, and then so I so the first question that comes to my mind, because I've done, it's funny, I for my thesis I did a simultaneous spin echo gradient echo where I shifted the echo times, and I did simulations, and I would do this sort of thing, and I would always, so I didn't get this far by any means. um, but my question is sort of along the lines of, I guess this is the art of doing the fingerprinting, and that is, so you have parameters such as the vessel sizes and the oxygenation, and it's assumed to be maybe random orientation. Is there any? I would worry that there's like non-unique solutions, like for instance, if you had a bunch of big vessels or some distribution of vessels at a certain oxygenation, is that the same as a bunch of different size vessels at another oxygenation? And is there non-unique, non-separable, solutions, like an inverse problem? Yeah,
Yeah, no, totally. I think you hit on the most challenging part of this because for it to be any good as a dictionary library, they should be orthogonal or they should be distinct from each other. And as you pointed out, not necessarily in our case, because deoxygenated blood volume, the amount of blood in a voxel that, for instance, is in veins and venules, right? If you have more deoxygenated blood volume, that might have the same effect as having more deoxyhemoglobin overall, right? So it is hard to disentangle. And the way that my collaborator Thomas Christen approached this problem was to inject contrast because that
yeah,
gives you another observation. It helps separate out the blood volume effects. We wanted to avoid that because we would like the vascular fingerprinting to be used dynamically to understand how other physiological parameters evolve with a stress test that we talked about earlier. So it's still a work in progress in terms of really characterizing how distinct are these fingerprints? How do we make them more orthogonal?
yeah,
I think we can use tricks like we've talked about adding phase information, adding prior information to help us down the line. And I'm optimistic that we will be able to, but I agree with you. Like that is the crux of the problem right now with
yeah.
the printing approach.
But it's a really fun problem, and I think that, right, I think you can make a lot of progress with this because you can do all kinds of fun things with the sequences, and the goal is just to separate things. It's like you could insert in multiple 180s to tune it to like smaller susceptibility compartments, or do all kinds of, yeah, I really, or maybe you could combine it in some way with maybe ASL, or who knows, or blood volume. Right, you can do all kinds of things. It's exciting
Uh,
just thinking about it.
yeah, I think we'll have to have a collaboration on
Yeah.
this. It sounds like.
Yeah, I really like it. And then right from those, and then you do this on a voxelized basis, and then out comes your map, and they're your parameters, and
Exactly.
that's awesome. That's so cool. Um, yeah,
One thing I will also mention is that we're trying to learn this sort of matching function also from whether it's a deep learning approach or like a Bayesian inversion approach. We're testing out different methods because we also just don't want to be limited by the discrete nature of our dictionary. I mean, I want to be able to look at a continuous way of all these parameters too. So I think there's also on the matching side a lot of ways that you can improve it. So both on the acquisition and the matching side, it's a really
well,
fun
that's
and rich
interesting.
problem. Yeah.
Right. Yeah, I even imagine things like adding diffusion weighting, and so I'm still thinking of the sequence side. But yeah, you're right on the matching side. Right, you can it's a challenging thing as well. Yeah. it's just, yeah, it's a wonderful problem. Yeah. And I think that, right, the power of that science paper over a decade ago was, I think that they were able to modulate the parameters such that the signature curves were more or less orthogonal. I mean, they overlapped a little bit, but then it can just be pulled out. But this is a richer problem. It's a more challenging problem, but I think it's really cool. Yeah, great.
Yeah,
Yeah,
I think one thing I like about it is also from the original Nature paper. I think the MR fingerprinting, not only are the fingerprints orthogonal, but it's orthogonal to things such as undersampling artifacts and motion, slight motion, noise, etc. Right? So if this is not part of your dictionary, if you haven't simulated it, then you won't be prone to these effects on your parameter maps, at
yeah,
least not directly. So it's possible that, not only do you get quantitative parameter maps, several of them, but that they might be more robust to noise and slight motion in a way that, the matching process rejects that because we haven't factored that into the dictionary.
interesting. Okay, all right. Yeah, that's right. Okay, that's an additional challenge. But that's great. That's cool. Okay, um, interesting. Well, good luck with all of that. And
Thank you.
I'll keep on thinking about that. Well, maybe I'll have to contact you. Not that we can really add much. I mean, other than, oh, try this or.
No, I mean, it sounds really exciting.
And then you have so yeah, I mean, even trying this at maybe 17 might help pull things out a little bit better. Who knows? But you don't have. We have a 7T, and you certainly can have
We'll
access to
have to fly
7Ts with your
over
collaborators,
some experience there.
your many collaborators. That okay. Sorry about that. All right. So this is great. This is great, and I think that I'm just trying to think of all the people in the world who are trying to work on this. I know that there's the MGH group, there's Stanford, there's Cardiff, I guess, where Richard Wise is, and yourself, and other people are Max Planck as well, but not too many. And I really, really do think it's an underappreciated sort of thing, because I feel that when people talk to me about how if fMRI will ever become clinically relevant, my feeling is that the whole physiologic side of fMRI is to me not necessarily lower hanging fruit, but it's sort of like people are doing work such as yourself to sort of already have clinically relevant data that extract useful quantitative information about that can't be obtained other than with PET or something. So so yeah, so I think that this is sort of, it's not fMRI, but it's sort of a version of it, but relying on oxygenation and things like that. So I think this will probably, hopefully, yeah, somebody has to do clinical trials and get FDA approval, and who knows.
Totally. And that's funny because I always get that question from people who aren't in the field, like, do you do MRI work or do you do fMRI work? And I mean, for me, it's both, because I am trying to measure brain function of some sort, maybe not with the bold signal, but I think you can also add on or extract, combine with the bold signal in a way that is more meaningful than the bold signal. But definitely
Yeah,
room to complement, the awesome work that the OHBM community is doing with the bold signal itself, whether that's multi-TE, high resolution, high temporal resolution. I think everything that we've talked about today in terms of really pinning down and getting some quantitative physiological information is only going to help your interpretation of the bold signal.
yeah, I definitely, I completely agree. It made me think of one last thing,
Go for
and
it.
and that is, there was a person I think that they're at Max Planck, and there was on one of your papers. I was trying to find it right here, but that actually looked at, and I was trying to think of intersections between using resting state and bold and whatever with what you're doing, and I was really, and I'm just kind of curious if you're aware of this or if you thought about it, was they were looking at resting state, just the latency, and comparing it with the global average latency. And it's not a quantitative measure, but they get these beautiful maps of with a person who has a stroke of, that show like the longer latency where the flow deficit is. And, I'm not sure how, it might compare well with gadolinium, but it's not quantitative. It might compare well with this. I'm kind of curious what your perspective on that is. If you're,
No, I think I'm familiar with the work you're describing, and I think it's an elegant example of where something that could have been an artifact, or again something that might have been disappointing, actually turned out to be a feature.
yeah,
So in a stroke or cerebrovascular disease setting, because of transit delays in different parts of the brain, if you do a zero lag correlation for resting state, if you don't shift the signal in one part of the brain relative to the other, I mean, there could just be a lag that you're not accounting for due to hemodynamics, due to the vasculature, and then you would miss the potential connectivity profile, right? So that's the kind of pessimistic way to look at it, but the optimistic way that you've described might have been my colleague, Dr. Ahmed Khalil.
yes, that
Mm,
was him.
perfect.
Yes,
Yeah, he kind of transformed that actually into a feature and used the lag, asking the question, well, I know I'm missing some connectivity because of hemodynamic delays. If I find the optimal correlation of these time signals, maybe that tells me about the relative vascular delay or hemodynamic delay between these different regions. And I think it works relatively well. I think this has been compared to, as you said, gadolinium and perhaps now even arterial transit time measures from ASL. I think it is an elegant way to look at transit delays. I don't know
yeah,
how it works, in a relatively healthier setting, but if we had other physiological information, and I think there are proponents of people measuring heart rate or respiratory signals in tandem with the bold, I could imagine similar sort of delay analysis being meaningful there in terms of
yeah,
characterizing physiological effects. So certainly I think that's a different dimension, the lag dimension that has
yeah,
own physiological profile and information. Yeah.
yeah. I even have a colleague who's doing like pulsatility and seeing,
Mm,
trying to measure cerebral blood pressure with
mm.
the different amounts. It seems like it's endless with MRI. It's a wonderful technique that keeps on providing interesting ways of looking at the brain and other organs, but brain seems like it's the easiest. But
It's the most interesting, but
yeah,
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 I'm biased.
exactly. Okay, well, with that, do you have any advice for any your people starting out, or as far as if someone were starting out and getting into like maybe I don't know, you were in the HST program, right, at Harvard, or were you in another? Uh,
I was actually in
MIT?
electrical engineering, but many of my lab mates during my PhD, as well as my supervisor, Alfar Edelsteinson, he was a faculty member in HST as well. So
Okay,
very
okay,
familiar with the program.
okay. But so, would you have any advice for you know what might be the best thing to get if someone's doing MRI or you know uh, even in general? I mean, any
Yeah.
sort of advice that yeah, what to do?
For me, I mean, this is definitely a general uh, sort of adage that I've kind of meandered by, which is do what kind of feels right in terms of the environment and the people. Because for me, at least, there's no reason to brute force a project or a particular analysis per se, unless you're excited about it, but also the people around you are excited about it. Like,
Yeah,
so I would prioritize happiness with the environment that you're in, and also to have feel good about the strengths that you bring to the table. I would say that one of my earlier anxieties as a early grad student was, am I technical enough, which is kind of silly, right, in retrospect, just because I mean I was thrown in an engineering program, but I had that worry. And I think there are just so many ways to contribute to MR research that we need all these perspectives to even make a dent on it.
Yep.
And I found that if you're purely technical or you're purely translational, like it's really hard to be in a silo or to think in one way.
Yeah.
So embrace your strengths, hold on to them, and really just see the people that will complement you in terms of expertise and also make you feel comfortable to pursue what you want to pursue. Right? Don't force it, but the right sort of collaborations that feel natural, that feel to your gut right, I think those are the ones that are going to pay off and also just, be fruitful in the long run.
That's great advice. That's really, yeah, because nobody can do everything, and you sort of have an environment, and you keep you work with people, and yeah, I mean, that's some of the best research is done that way. I agree. And so, well, thank you very much. I really appreciate this, and
It's been a
yeah, I hope
blast,
more.
Peter. Thank you.
Oh, well, thank you. I hope more people will keep on doing this, and I look forward to your next papers and continued success. So, thanks.
All right. Thank you.
All right, thank you.
Neurosalience is brought to you by Organization for Human Brain Mapping. This episode is produced by Ömer Faruk Gülban and Alfie Wern.